Our computers have memory to store data. Data stored in memory is read, processed, and stored by the CPU. Memory consists of several spaces with a fixed size to store data that the CPU can process. And one space consists of several bits representing a fixed size. Bits can store 0 or 1. So, countless zeros and ones are stored in the computer memory we use. The same goes for the number 5 we are dealing with. 5 is converted to be expressed as 0 and 1 and then stored in memory. How is the number 5 represented by 0 and 1? How would the decimal number 5 be represented in binary? Here, instead of doing it the hard way, you can use Python's bin function to convert. Therefore, the decimal number 5 is 101 in binary. The binary number 101 converted in this way can be stored in memory. To summarize, in order to store a number in memory, it must first be converted to binary. Then we put it into each bit of memory starting from the back. 101 requires 3 bits in memory like this. If one bit is reduced and only 2 bits are used, there is no space to store the first one of 101. Now, let's consider a 4-bit memory to store data. Each bit of memory can contain either 0 or 1. If you put 0 in all bits, it represents 0, 0, 0, 0 in binary, which is 0 in decimal. If you put 0, 1, 0, 1 in 4-bit memory, it is the same as representing 5 in decimal. Finally, if we fill them all with 1, we get 15 in decimal. So filling all bits with 0 can represent the smallest number 0, and filling all bits with 1 can represent the largest number 15. The largest number 15, when expressed as a power of 2, is 2 to the power of 4 minus 1, and the number of numbers that can be expressed is from 0 to 15, a total of 16. 16 can also be expressed as a power of 2 as 2 to the 4th power. If we generalize this, n-bit memory can express a total number of numbers raised to the n power of 2, with the minimum value being 0, and the maximum value being 2 raised to the n power minus 1. To recap, in a 4-bit memory, the number 5 is converted to the binary number 101 and stored in each bit. In this case, the number 5 is an unsigned number that only represents size. Among numbers that only have size, integers are called unsigned integers. So size 5 was 101 in binary. How do we express minus 5 in binary? Moreover, the binary number 101 does not always mean plus 5. So far, we have used all 4 bits in 4-bit memory to represent numbers. However, one additional bit is needed to express signs such as plus or minus. So we use the most significant bit to express the sign, and the remaining bits to express the size. An integer that can express a sign by assigning a row to each bit is called assigned integer. Let's come back to the 4-bit memory space. Even if the most significant bit is used as the sign bit, the fact that each bit can only store 0 or 1 does not change. However, the only difference is that when the sign bit is 0, a positive number is expressed, and when the sign bit is 1, a negative number is expressed. For example, let's store minus 5 as a signed integer in 4-bit memory. Minus 5 is a signed integer with sign minus and magnitude 5. First, add 101, the binary form of the number 5, to the 3 bits representing the size. Then, 1, which represents the negative sign, is inserted into the most significant bit. That is, the signed integer minus 5 is stored as 1101 in 4-bit memory. After all, plus 5 and minus 5 are binary numbers that differ only in the most significant bit. However, there is a bit of problem. If you have plus 5 and minus 5 expressed as assigned integers, what will be the sum of the two numbers? First, if you add two numbers using decimal notation, the result is 0. However, if you add two numbers expressed in binary, you get 0010. The binary number 0010 represents 2 in decimal. You can see that the result of binary addition and decimal addition are different. To solve this problem that arises when simply using the most significant bit as the sign bit, there is an alternative way to represent signed integers. It's called 2's complement. Let's express the signed integer minus 5 as 2's complement. To express in 2's complement, first, convert the magnitude part to the binary form of the unsigned integer, and flip every bit. Bits that were 0101 become 1010, and add 1 to the result. The flipped bit 0101 becomes 1011 by adding 1. This result is minus 5 expressed in 2's complement. Let's go back to the addition problem from earlier. The result of adding binary numbers is always 0. This result is the same as adding decimal plus 5 and decimal minus 5. One of the most important points is that the same binary number has a different meaning when representing a signed integer than when representing an unsigned integer. For example, the binary number 1011 is minus 5 in 2's complement representation, but it's 11 in unsigned integer representation. To summarize, in 4-bit memory, the smallest negative number of a signed integer in 2's complement representation is minus 8, and the largest value is 7. To generalize this, the 2's complement representation of a signed integer can represent minus 2 to the n-1 power to the n-1 power of 2 minus 1 in n-bit memory. On the other hand, in 4-bit memory, the smallest unsigned integer value is 0, and the largest value is 15. Generalizing this, as we saw earlier, in an n-bit memory, the minimum value is 0, and the maximum value is 2 to the n power minus 1.